Hi, my name is Taylor Robnett, and I'm the lead for Group 4, and I'm going to be presenting the Injury Performance Lab. All right, so we're basically looking at internal combustion engines, and we all know that they pretty much convert basically a gas mixture, or the energy within a gas mixture into mechanical energy. And so there's several different types of engines that we can use to do that. Reciprocating, rotary, spark compression, ignition, 2-stroke and 4-stroke. And for this lab, we're going to be using a 4-stroke, which is a combination of reciprocating and spark ignition. So this is kind of what we're dealing with. The first stage is an intake or a suction stroke, and then the second stage is compression. There's going to be a spark, and then we're going to go into an expansion or a power stroke. And then the very last stroke is the exhaust stroke, which pushes the gas fume out of the cylinder. So our objectives for this lab are to kind of analyze engine performance under different circumstances. The first case is going to be a constant speed variable load test. Sounds just like it sounds. We're going to run the engine at a constant RPM and then subject it to different loads. And then the next test will be a constant load with variable speed. So we'll put the engine under a load and then change the RPM. So this is what a PV diagram of an ideal auto cycle looks like. You can see here from basically, if you want to call this 0, from 0 to 1 is your suction stroke. From 1 to 2 is your compression stroke. From 2 to 3 is the ignition. 3 to 4 is the expansion. 4 to 1 is the heat rejection, and then you go back from 1 to 0 is your exhaust stroke. This is idealized, like I said, from 1 to 2 and 3 to 4 is an isentropic process. I think they're also considered adiabatic. But this is the actual real auto cycle. As you can see here, nothing is ideal about this. You've got all kinds of, it's not an isentropic process, it's not an adiabatic process. You've got all kinds of losses. So this is what we're getting. So for the equipment that we're going to use a 13 horsepower motor. Here's some information that we're probably going to need for the calculations for this experiment. We're going to use 87 octane gasoline. Some more information that we're probably going to need for this experiment. Here's our apparatus. Probably can't see it very well. And the way we're going to conduct this experiment, we're going to use a water brake dynamometer. Hopefully I said that right. It's basically a device that has a chamber, and within that chamber there's a propeller, and we're going to be running water through that chamber, and the engine is going to be rotating the propeller, and then based off of tachometer and torque meter, we'll get readings out on what the RPMs are versus the torque that's generated by the engine. You can see almost all horsepower. Turning the rotor is converted into a temperature change in the water. Here's some equations that we're going to use to calculate the information on the engine and for this lab. We got air mass flow, volume efficiency, conversion efficiency, mechanical efficiency. This is the brake mean effective pressure, and then of course power. A over F or F over A is actually the fuel to air ratio. Not horsepower is actually related to torque and the RPMs over 5252. Horsepower is dependent on both torque and RPM. It's important to understand that. To understand basically the results of this. So here is a torque and horsepower curve versus the RPM. As you can see, the torque curve has a peak right here. This isn't technically for our experiment, but it's just off of an example I used. When engineers design engines based to operate at a certain torque or have a high efficiency at a certain torque, So that's why you have one peak here. It can vary depending on what the design is. And then as you can see here, this power curve has a peak that's slightly higher. That's because in this equation right here, you have the horsepower equals torque times RPM. At a certain point, your torque will actually become less efficient, or your engine's torque will become less efficient. The torque will go down, but the RPMs will actually increase. So at some point, horsepower and torque will equal, and then after that point, horsepower will actually overcome torque, and that's because of your RPM speed increasing.